Hey everyone, welcome to the video for 3.7 improper integrals. So if you've made it this far, congratulations, you're about at the halfway mark for the course. So give yourself a pat on the back. For improper integrals, it's going to behave very much the same way as definite integrals or improper integrals, except we're just going to have a limiting process. So notice in the definition on number 1, the improper integral is, well, it's called improper because the upper limit of integration is infinity. And so the way that we do this is we kind of give ourselves a dummy variable, in this case, t. I personally use b, just an old habit. But you give yourself a dummy variable, integrate as normal as you would any other definite integral. And then the limit as t goes to infinity, that goes on the outside. And then so once you've integrated and evaluated your definite integral, then you do the limiting process. So in 1, we have the upper limit is infinite and the lower limit is finite. And 2, flip that. In 3, we have it's infinite on both upper and lower limits. So you can actually split this. Notice in equation 318, they split it at 0. You can actually split it at any point. Like I could have done negative infinity to 1 million plus 1 million to positive infinity. So it's your choice. 0 is just a nice, easy, convenient number. The other thing to notice about this definition is that f of x is continuous on the interval everywhere. So there's no kind of like divisions by 0 or anything like that. So let's start with example 3.47. So all we're going to do here is just rewrite this. So if we want to know the area, we're just going to integrate f of x over the interval given. So the area equals the integral from 1 to infinity of 1 over x dx. And on this interval, f of x is continuous. So all I need to do is just write this as the limit as your dummy variable goes to infinity, 1 to the dummy variable, which for us is b, 1 over x dx. And then I integrate as normal. So keeping the limit, but not yet evaluating the limit. This is going to be the natural log of x evaluated from 1 to b. And again, in this step now, I'm still not evaluating the limit. But I'm just going to use the fundamental theorem of calculus part 2. So this is going to be ln b minus ln 1. Which is just the limit as b goes to infinity of the natural log of b, because this is 0. So as b goes to infinity, the natural log of b will also go to infinity. That's it, that's the whole problem. So let's try another one here. Again, f of x is continuous everywhere actually, but we only really care about the interval from negative infinity to 0. So f of x is continuous on its interval. So I give myself my dummy variable, b, and I let b go to negative infinity. So I'm going to take my integral from b to 0 of 1 over x squared plus 4. And hopefully by now you recognize this as ½ arctan x over 2. And we're evaluating that from b to 0. So we will plug in those values. And then once we've done that and simplified, then we'll take the limit. So this is going to be 1/2 arctan of 0 minus 1/2 arctan of b. So arctan of 0 is 0. So the simplification, if I'm really going to belabor the point, the simplification is 0 minus 1/2 arctan of b. So I'm really just taking the limit as b goes to negative infinity of negative 1/2 arctan. And if I don't want, oh, I made a boo-boo. This should be b over 2, right? If I really don't want to fuss with this negative 1/2 business, I can always pull scalar multiples out. So I could have negative 1/2 times the limit as b goes to negative infinity of arctan b over 2. So this is a composition of functions. So as b goes to negative infinity, b over 2 will still go to negative infinity. And arctan of air quotes negative infinity is just negative pi half. So this is negative 1/2 times negative pi half. So this is pi over 4. So far we haven't had to do anything tricky. We haven't done any L'Hopital's, we haven't done any integration by parts. So if you were wanting to see that, get ready. So in this instance, we have it where the upper and lower are both infinite. So the way that you split this up, again, you can choose any value that you want, but 0 is typically the most convenient. So we're going to have, the first idea is that we just split up the integral. And then from here, now we can write it as something involving the limit. So we want to do limit as b goes to negative infinity of b to 0 x e to the x dx. Plus, I can use the same dummy variable. If you feel like maybe that's confusing, you're more than welcome to use a different dummy variable. 0 to b, x e to the x dx. So now we need to integrate. And this is an integration by parts. So the first thing I want to do is I just want to get the form for x e to the x dx, right? Like I don't want to worry about the limit or the limits of integration yet. I just want to get the form for this using integration by parts. So if I have an integral of x e to the x dx, then using my ILH, the x is algebraic and e to the x is exponential. So I know that I'm going to let u equal x so that du becomes just dx, and then I'm going to let dv equal e to the x dx so that v is just e to the x. And so now that I have that, this will equal u times v, which is x e to the x, minus the integral of v du. So that's e to the x dx. So what I get is x e to the x minus e to the x plus c. The c is inconsequential here because we have limits of integration, so that will go away. But in general, this is the form for the integral of x e to the x. So now that I have that, I'm going to steal this guy. And I'm going to Oopsies, that's not what I wanted to do. And I'm going to rewrite it as the limit as b goes to negative infinity. But this time now I know what my form is. So this is going to be x e to the x minus e to the x evaluated from b to 0. And then to that, I'll add the other limit, e to infinity of x e to the x minus e to the x from 0 to b. And then once I'm here, I'm still not evaluating the limit portion yet. I'm just going to plug in the zeros and the b's. For the first one, this is why 0 is a great choice, by the way. So for the first one, we can see that that x here annihilates the whole x e to the x part. So this is just going to become -1 minus b e to the b minus e to the b. And then similarly over here, we're going to have the limit as b goes to positive infinity of b e to the b minus e to the b minus, this gets annihilated by 0, and then so it's just -1 here. I'm going to do these separately. I'm going to call this number 1, and I'm going to call this number 2. So for number 1, we're looking at the limit as b goes to negative infinity. Of -1 minus b e to the b minus e to the b. So this is going to take some algebra and also L'Hopital. So I can split the limit into sums. Like the limit of the sum is the sum of the limit, provided that both limits exist. So I'm just going to flip this -1 out, and then I'm going to subtract the limit as b goes to negative infinity of b e to b minus e to the b. And then the next thing I'm going to do is I'm going to say that this equals -1 minus the limit as b goes to negative infinity, and I'm going to factor out e to the b. So I'll get e to the b times b minus 1. So as b goes to negative infinity, what happens is that this will go to 0, and this will go to infinity. So we have a 0 times infinity situation, and we know how to handle that. We kind of cleverly flip this 2 times. So it's -1 minus the limit as b goes to negative infinity of b minus 1 over e to the negative b. So algebraically, these are equivalent. But when we do this, what happens is we get, again, this is like, plus and minus, okay, negative infinity, whatever. So now this is negative infinity over, so notice that b is negative. So this really is e to the infinity. So this is infinity over infinity. So now we can use L'Hopital's rule, which is why we did that before doing this lesson. I'm not doing L'Hopital on the -1. I'm just doing it on the limit stuff. So -1 minus the limit as b goes to negative infinity. And now I'm just taking the derivative of top and bottom with respect to b. So this is going to be 1 over negative e to the negative b. As b goes to negative infinity, this just becomes 1 over negative infinity. And the denominator getting so large in magnitude just forces this whole limit to be 0. So this is just -1 minus 0, which is negative 1. So this guy was equal to negative 1. Now we can look at the second piece. We're taking the limit as b goes to positive infinity this time of be to the b minus e to the b plus 1. And again, I can pull that 1 outside of the limit because it doesn't have a variable in it. So it doesn't affect anything. Plus, we have this idea that the limit of the sum is the sum of the limits, provided they both exist, blah, blah, blah. So I'm going to do that. I'm going to say that this is the limit as b goes to infinity. And I'm just going to go ahead and factor now. This is e to the b times b minus 1. And the 1 is completely outside, like it's not even messing with the limit at all. So now we're right back into this kind of familiar territory, except b is going to positive infinity. So if b is going to positive infinity, then this goes to infinity. And infinity minus 1 is also infinity. So if I take two numbers that are positive and they both go to infinity, and I multiply them, well, they're just going to infinity even faster. So this is really just like infinity plus 1. So this diverges. If one piece diverges, the whole thing diverges. Like there's no saving it. Because there's nothing I can really combat this with. Like if I subtracted 300 bajillion from infinity, it's still infinity. So the moral of the story is that this whole thing diverges. Because one piece diverged, particularly the blue piece. So this integral x e to the x dx was infinity. So now we're going to move into territory where f of x may not be continuous on the interval. And we're going to look at that first when it's not continuous at the endpoints. So f of x may be continuous just up until a point b, but not really at b. You're still going to give yourself that dummy variable, but now it's going to be a one-sided limit. So notice that if you're at a, which is before b, and you go up to b, then that's a left side limit. It's going to be your dummy variable approaching this endpoint from the left. And then similarly, you'll have a right-sided limit as well. The other option is that maybe the discontinuity occurs. So yeah, write this down. So here, the discontinuity occurs at endpoints. And in the other case, the discontinuity occurs somewhere in the interval. So here is the discontinuity occurs inside the interval. And so when the discontinuity occurs inside the interval, instead of before, like I was like, oh, you can make it 0, you can make it whatever, you just have to split it. When the discontinuity occurs inside the interval, you have to split it at the point of discontinuity. I'm just going to scroll up to the original definition when we had a continuous function. In this case, you could So x equals 0, again, just used for convenience, but you are allowed to choose wherever you want. Like I said, you could have made that like 10 million. Okay, so when you have a discontinuous function, your hand is forced. So let's see what that looks like. Let's start off with a discontinuity at the endpoint. So we have our discontinuity at x equals 4, right? Because that would give us a division by 0. So what we want to do is give ourselves the dummy variable. And let's think about this. So we know that the limit has to go to 4. But if I'm at 0 and I'm going towards 4, that means I'm approaching 4 from below. So the left-sided limit as b goes to 4, or the limit as b goes to 4 from below, however you like to say that, of 1 over the square root of 4 minus x dx. So just in general, if I have this integral, you're more than welcome, if it's really obvious what the integration will be, that's fine. If not, I would do your u sub, let u equal 4 minus x, then negative du equals dx, right? Because your du is negative dx, so I just brought that over. And then what happens is I'm going to have negative 1 over root u du, and then this should be negative 2 root u plus c, so negative 2 square root 4 minus x plus c. So that's our general form for this integral. I find it's easier to work it out without all the busyness of the limits of integration and then the limit in front of that. I do it separately off to the side. So that way I don't have to kind of keep track of so much notation. So bringing that integral over here, I get b going to 4 from below of negative 2 root 4 minus x evaluated from 0 to b. You're more than welcome to bring that negative 2 outside of the limit because it's a scalar multiple. I'm kind of being lazy today, so I'm not going to. So this is the limit as b goes to 4 from below. And now I'm just applying the fundamental theorem of calculus part 2. I haven't evaluated any limits. So I get negative 2 square root 4 minus b minus negative 2, so that's plus 2 root 4 minus 0. So simplifying again, before I evaluate the limit, I'm going to have negative 2 square root 4 minus b plus 4. I could flip the 4 out, that's fine. If you bring the 2 out at this point, just be careful with your algebra and factoring. So as b goes to 4 from below, this is going to be, the radicand will remain positive and it's just going to go to 0. So what's going to happen is that this is equal 0 plus 4, which is just 4. And then that's your answer. So let's do another one with a bit more complexity to it. We didn't learn L'Hopital's for nothing. So now we have the discontinuity on the lower limit of integration. So here we see that epsilon x is discontinuous at x equals 0. So what we want to do is, again, with the dummy variable, but the integral from b to 2, that's everything above b and less than 2. So I want to approach 0 from above in this situation. And then I have epsilon x dx. And this is another super fun integration by parts. So as before, I'm just going to consider the indefinite integral without all of this extra noise. x ln x dx, and I want to get the general form. So if I use isolate, I know that my log is going to be ln of x. X is algebraic. So u equals ln x du equals 1 over x dx, dv equals x dx, and v equals x squared over 2. So then what I get is uv, which is x over, I'll write it like this, 1/2 x squared ln x minus the integral of v du. So that's going to be x over 2 dx. And so this just equals 1/2 x squared ln x minus x squared over 4 plus c. So now that I have my form for the integral of x ln x, I'm going to use it here. So I get the limit as b goes to 0 from above of 1/2 x squared ln x minus 1/4 x squared, and I'm evaluating that from b to 2. So now I'm going to apply FTOC part 2. I'm still not evaluating this limit. It's just chilling, but we have to write it, otherwise the equality is not true. So I get 1/2 times 4, so that's 2 ln 2, minus 1/4 times 4, minus 1, minus 1/2 b squared ln b minus 1/4 b squared. Two ln 2 minus 1 doesn't really do anything for me in terms of like affecting my limit. So I'm going to flip it out. I'm going to say this is 2 ln 2 minus 1 minus the limit as b goes to 0 from above 1/2 b squared ln b minus 1/4 b squared. And again, we have the limit of the sum is the sum of the limits, provided both limits exist. So I'm going to go ahead and split this up one more time. I'm going to write this as ln of 4 over e, just because I can, and it's less writing. These are equivalent, by the way. Minus the limit as b goes to 0 from above. Oh, you know what I'm going to do? Be super sneaky. I'm going to flip out this 1/2 as well. So then I'll get b squared ln b. And then it's going to be minus and minus, so it's plus 1/4 the limit as b goes to 0 from above of just b squared. So ln 4 over e, that's a number. Looking at the end, a limit as b goes to 0 of b squared, that's just 0. So the thing that's really giving me grief here is just this b squared ln b, because this is going to be 0 times infinity, right? So I can use L'Hopital's here, and I'm just using L'Hopital on this guy. I'm not using it on the 1/4 ln b to 0 b squared, because that's just 0. And also I can't, because it's not in an indeterminate form. So I still have ln 4 over e, and then I still have this negative 1/2. But now, oh, I haven't used L'Hopital's yet. jump in again. Now I'm going to rewrite this troublesome limit in a way that will allow me to write L'Hopital. And the way I do that is ln b over 1 over b squared. Right? Or I can write b to the negative 2. Either is fine. And then this was just 0, by the way, so I'm not going to write that. So now what happens here is that this goes to negative infinity, and this also goes to infinity. So now I can write this, rewrite it with L'Hopital. So applying L'Hopital, I'm not applying L'Hopital to anything other than this business right here. So I still have ln 4 over e. I still have my 1/2 out in front, but the L'Hopital action occurs here in this step. The derivative of the natural log of b with respect to b is 1 over e. Oh, I just realized why they use t. T has, it's like more recognizable, I guess, as a variable. Like x, y, z, w, u, and t are kind of like the variables, theta, so that one in there. And like a, b, c are kind of the more constants. But I mean, that's not like a rule, so I'm going to stick with b. Okay, that was the derivative of ln b. The derivative of b to the negative 2 is negative 2 over b. Or I was going to write negative 2 over b cubed. I'm just, yeah, no, I am. I like that better. Negative 2 over b cubed. So I'm kind of switching up to negative exponents and positive exponents with a fraction, but whatever. So now I can kind of see what happens here. So as b goes to 0, this is going to be, oh, well, actually, we can do something else first. 4 over e minus 1/2, the lim as b goes to 0 from above. So we can totally simplify this. So this is going to be b squared over negative 2, I want to say. So as b goes to 0 here, then boom, this guy goes to 0. So what we're left with is ln 4 over e, or if you want to write that as 2 ln 2 minus 1, I don't really care. But that's it, that's the limit. We did it, it's done. So we just have one more case to cover. And that is when we are discontinuous in the middle of our interval. So for this one, we can see that we have the discontinuity at x equals 0. So in this instance, we have to split at 0. So the first thing I'm going to do is negative 1 to 0 of 1 over x cubed dx plus 0 to 1 of 1 over x cubed dx. And now we're right back in that familiar territory where we're just discontinuous at the endpoint. Maybe that's a bit hard to read. So I'm going to give the dummy variables again. So b going to negative 1 from above. B to 0, 1 over x cubed dx plus the limit as b goes to 0 from, what are you thinking? Sorry. Zero from below, plus the integral of b to 1. And so now I'm going to 0 from above of 1 over x cubed dx. And so just in general, the integral of 1 over x cubed dx is going to be negative 1 over 2x squared plus c. So I'm going to use this and then I have this other guy that takes the same form. Okay, so now fundamental theorem. Again, I haven't done anything to evaluate these limits. I'm just doing the algebra, the integration and then the subsequent algebra. So this is going to be negative 1 over 2b squared. And then I'm going to minus, like the negative 1 as my lower limit becomes a positive 1, but I'm still minusing a negative. So it's going to be plus 1/2. And then this one becomes negative 1/2 plus plus 1 over 2b squared. So what's nice here is that if either one of these diverges, the whole thing diverges. We saw that before when the function was continuous. So what happens is I just need to, like, as soon as I find that one diverges, then I can just be done. And in fact, we can see this right away. As b goes to 0 from below, this thing's going to blow up. So this diverges. In fact, they both diverge. So the whole thing diverges. And that's it. That's our last example. So good job finishing out the second week of the course. And if you need me, please send an email or post to the forum.